Okay. The reason we're doing a video recording today is because the content for this week and next week is in some way quite difficult, and but it will not appear in the final exam. Okay, just to be clear, if you don't understand it, that's perfectly fine. Okay, and then some of you I know are from, probably two of you are from Olivier's group in physics department, and then you guys will find this extremely useful. Okay, probably appear everywhere in your thesis. And then I know some of you are from Andrea's group, and if you're working on single photon detector or photon number resolving detectors, that will also be helpful to you. Okay, and of course some of my students will find useful, and of course, if it's, well, we talk a lot about photon, and maybe some of you will find photon itself, like how to express it mathematically. What's a photon? That's something important we can talk about. Okay, so previously we say, we have a two-level system. We have input E cosine t. Okay. Previously, we say this is a semi-classical picture. The classical part is on the EM field. Okay. We use Maxwell equation for this part, and the quantum part is for the electron. Okay. It has energy level. And today the task is really about quantize this thing. Okay. We no longer use Maxwell equation. And it's not there's something wrong with Maxwell equation. It's just there's some phenomenon fundamentally you can't explain with Maxwell equation. For example, last time, I think a few weeks ago, we derived when you complete one Rabi flip, where your atom rise from ground state to excited state, you emit, you absorb energy of h bar. You absorb energy of h omega, right? And we say this is an energy of one photon. But classically, there's no such a concept because the transmission, the absorption in a classical picture is continuous. Okay, you're taking energy a little by little, and finally, when you move all the way up to here, you absorb one photon. You absorb energy of h bar omega, which we know is one photon. Okay. But classically, there's no way to say that, a photon is, I think classically you can even say there's a half a photon energy being absorbed, which is later people find out it's not true. It's not correct. Okay, so this is one thing. The other thing is we go back to this very the idea of when the photon was proposed by Albert Einstein, right? You have a metal, you shine some light, and then the free electron inside can absorb that light and escape, create a current, right? Photoelectric effect. Okay? And what people find out at the time in experiment is that, classically, we think if the energy is continuous, then if you have a really high energy, no matter what the frequency is, you have the probability of getting out some electrons, right? But what people find out is that there's actually a threshold. Let's see how we write it. There's a threshold frequency. Below the threshold frequency, there's no current at all. So you can't really get electron out. Okay? So at that time, Einstein kind of inspired by Planck's idea that the energy has a minimum amount. And he argued that for the photon, for the light, although it's traveling like a wave, the energy has a minimum pack. The pack is h bar omega. it kind of makes sense if you think about it. If we say like electron, you can't divide electron into half an electron, right? You can't divide, you can't divide proton into quark, but it's not something we discuss. Okay, so there's some fundamental element, fundamental particles that you can't divide any further. And so it's actually, and if we know m equals, E equals mc squared, the same velocity should apply to energy as well, right? If you can't divide your particle further, you can't reduce your mass by half, then probably you can't divide your energy by half. So although the idea seems kind of, contradicting to our intuition, but if you think about it, it actually makes sense. So this is where people stop around 1906, 1907, 1906, and because they don't have the tool to do it mathematically. And then it was after Schrodinger proposed the Schrodinger equation, and then I think the first people figure it out is either Schrodinger himself or Pauli. Okay, I have to read a little bit more about the history if I want to know this. So they introduced something called, so first, the logic is when they took the Maxwell equation and then they somehow write it down the Hamiltonian. Later we will see how to do that. They write down the Hamiltonian and then they solve the eigenstate, and then they see something like this. The eigenstate is, okay. They saw that. So that's kind of the first way to derive, one photon energy is h bar omega. Okay, but then mathematically it's difficult to use. Later we'll see mathematically this one is good for our understanding, but we shouldn't stop there. And then I forgot who did it, but it should be Pauli or Schrodinger. They did something called second quantization. So this is something pretty deep in quantum mechanics. Normally you won't learn this in quantum mechanics class unless you take advanced quantum mechanics class. Okay, the second quantization is actually the foundation of particle physics. Okay? How you describe a particle is actually the same way of how you describe a photon. Okay? So after these 2 weeks, later when you read like any high energy physics papers, you will at least understand their first equation. Their first equation is usually Hamiltonian written in a second quantization form. And you'll be able to see what it means, but as long as they move to a second equation, normally at least I would be completely lost. Okay. So let's start it. And we want to restrict ourselves, want to give us some constraints so that our situation is a little bit better than try to. Well, the ideal way is you do a very general quantization of photon, like light in free space. But then that's actually pretty hard. The hard part is not in physics, it's mainly in mathematics, and I don't think it's worth it. And then for most of today's research, well, I shouldn't say that, but for a lot of you in ECE, the research is not really in free space. Okay, so first we restrict ourselves to photon in a pair of mirror, fiber pearl cavity. So why we want to do that? 2 reasons. Well, later you will see why, but really 2 reasons. One is to, it's always hard to consider things in infinity and minus infinity. Okay, it's hard to, well, because if you have, let's say you have E minus I k z, you can't say at infinity this is 0. Okay, so there's so mathematically there's some trouble there. Okay. And the second thing is, once you put, let's say, put some light inside, you're propagating this direction, hit the mirror, coming backward. what this would do is this will create a standing wave, right? So let's say this direction to the right, if you write it down as E minus I omega t plus I kz plus E plus I omega t minus I kz. And then the reflection would be E minus I omega t. K is a wave vector. It represents the direction, right? This will be minus K ikz plus E plus I omega t plus ikz. Right? Makes sense, right? And if you write down E, right? E is a sum of propagation to the right and propagation to the left. It's a linear combination of these two. And then what you can do is you can see for the minus I omega t term, these two can sum up. It goes to, okay. And this one we know is cosine kz, right? 2 cosine kz. The same apply to this part. So you have E minus I omega t cosine kz. Probably there's a 2 here. Okay. And this might look trivial, but think about it, what we do here. Previously, we have to, well, if this is free space, we have to write like this. Okay. Now what we do is we kind of separate. Let's write it this way. Plus 2 E I omega t cosine kc. Now what we do is that previously, I omega t is plus I kz. This one is minus I kz. Okay, so kind of omega, well, t and z are multiplied together. You can't separate them. So right now, what you can do is you can write down E, a function with time, times cosine kz. This is a separation of variable. And then in differential equation, this will be extremely useful, right? If you're able to separate your spatial variation with your time variation, then you can build up 2 independent equations. Okay? You don't have to worry about, calculating both terms. And this is the major difference between a photon in a cavity, a light in a cavity, and light in free space. Okay. So we do this, and then because we can always adjust the phase, we can always adjust our phase of the light inside. You can choose a z, right? You can choose the initial point. So for simplicity in this class, I think we will write down let me further define something. Okay. Okay, sine. Sine is, later you will see sine is because you take derivative, it's cosine, and then there's no minus sign in the front. Okay, that's the only reason we take sine. Okay, you can always choose your 0 point of z to adjust your cosine into sine. Okay, so it's not a problem. And then the next thing we want to figure out, we want to kind of make a good definition, is about the direction of your E field. Okay. The propagation direction, this one we call it Z. Okay. And then we want our E field to oscillate in X direction. That means the E field is like this. Right. And then Y would be here. Yep. Okay. And then the rest of Y direction, if you're familiar with Maxwell equation, would be the direction of magnetic field. Okay, they're perpendicular. So you will have magnetic field like this. Okay. So this is just simply to define a coordinate to make your life a little bit better. Okay. So we write down Ex. Okay, E is our direction. And then we know because it's a resonator, K has some constraint. Okay. K, suppose inside it's all air, there's no dielectric material. K is 2 pi lambda. And then for resonator, we know m times lambda equals L. Right? You need the L is the L is the length of your resonator. In fact, if you want to be a little bit careful, you can put 2L here. It's like finish one round trip, it repeats itself. So we know that K is pi m pi L. Okay. So you know if you really want to know what is K, there's a number you can use. Okay. So this is again an advantage when you compare with light in free space. The K is kind of random here. You can select the K. Okay. Now this is all classic. We just define the coordinate. And next, the thing we do have a little bit connection to quantum, but not really yet, is to write down the energy, or we say Hamiltonian, the energy of the EM field. Right? The energy of the EM field, we know the energy density is right. This is the energy density, the energy of EM wave per unit area. So for resonator, right, its total energy, you have to do integral, right? On x direction, y direction, z direction. This will be the energy of your system. Still classical physics. Okay, there's nothing quantum here. Classical physics. Okay, give you a E field, and then you tell me how much energy inside a Fabry-Pro cavity. Nothing very fancy. Okay, so first thing we want to calculate this. Well, we have a definition of E, so probably we can do that. The second thing is we need to consider what is H. Okay, H, of course, we know it's connected by Schrodinger. Well, no, by Maxwell equation, right? We have okay. So later we can use this to express H as a function of E. So later this equation will only have E field, because when we calculate light and matter interaction, we only use E field, like at least in our class. Okay, so if we look at H and we don't have H here, don't worry, we can tackle this later. So now let's work on this integral first. And the direction we want to go, is that if we go randomly, we just calculate the h, you might get lost. Okay. I believe when the first people who kind of work on this problem, he already have in mind that the harmonic oscillator, right? The harmonic oscillator has eigenenergy like this, right? It's like quantized. Each harmonic oscillator we call it phonon, but if you want to add a little bit more energy, you have to add h bar omega, just like photon. Okay, so I would guess the first person who wants to solve this problem will try to express the Hamiltonian in a way that it looks very like the Hamiltonian of a harmonic oscillator. Right? Then you can very straightforwardly borrow the solution from the harmonic oscillator. Okay? You don't have to work out all the math again. And also you can check if it's possible to do it this way. So let's write down harmonic oscillator. Okay, here we didn't use K because we know the K harmonic oscillator. This is the spring. Okay, it's not the wave vector. Okay, this one replaced the kx squared. Okay, it's the reason we do it is because you can't find a spring in the light, so you have to replace something you can draw attention to. Okay. So one thing, well, if we look at here, then it kind of makes sense that we want, well, x squared, we probably can't have that, e squared. There's a square term here. And then we can define something we want, m. Okay. So so let's do it in this way. Okay. We define E as Ex. Okay, its direction. Sine kz. Kz will somehow disappear when you do the integral. Right? When you do the integral of z, then it becomes a number. Okay. And then we want to have a variable q. Well, if you know analytical mechanics, you know q is actually x. Okay. You want a variable that has the same kind of, you understand it as displacement. Okay. Q is the thing you want to draw attention to. When you write down h, you want to compare x to q. Okay. You just define a variable like q. And then the next thing is there will be something left, right? Everything that's left, we call it A. Okay. Here we didn't do much. We just say we define something. We want it to look like this. And then it's Q. Okay, that's it. And then we do this integral. And then when we make this integral look like this, we know what is A. Okay, A is the remaining part. So we do this integral. So first direction goes away, it doesn't matter. Q is a function of time. Will it interfere with the spatial integral? And then A is a number, right? Comes out. doesn't matter at all. Okay, and you have sine square kz dx dy dz. And this integral, we kind of know the result, right? Sine, we say about this sine, the average of sine square is half. So what this will give you is L divided by 2, right? You integral from 0 to L, and then sine squared, the average value is half. Okay? And then dx dy kind of represent the cross section, okay? The cross section of your resonator, of your cavity. So it's we can call it S, the surface area. Okay, there's an area how large a mode is, right? If you know, if you use, for example, if you use single mode fiber, and you place 2 mirrors here, and for single mode fiber, you know this is roughly 8 micron. Okay, this is something you can calculate when you build your resonator, right? When you build your cavity, you know this. So we can write it down a little bit better. Half is good. We don't want to lose this half. And then L times S, well, length times area is volume, right? Length times area is volume. So this is the volume. It's not the volume of your cavity, it's the volume of your mode, of your light mode, okay? Again, if it's if it's a single mode fiber, your mode is confined here, and then you have a mirror, you kind of know what the volume is, okay? V is the volume of your mode, of your light. It describes what's the size of your light, okay? You can build a really large mirror, but if your light is very focused in the center, then the S is small, okay? This is the volume, epsilon V. Okay, you have the 2 here, A squared, Q squared. Right? It looks a little bit like this. At least you have square term. So the next thing we do will be restart the camera. Sorry.
That's a quick question.
Yes.
It might be a small point, but the way you've drawn it, it looks like the E field and the B field are out of phase with one another by pi over 2.
Yes.
I think they should be in phase with one another.
It should be out of phase, right?
I've been looking at pictures and they're all in phase.
My thinking is, well, I'm not sure in resonator what it looks like. I have to think about it, but in resonator is, but if it's free space, then what out of phase, in phase would have a problem is that at this point you have a very high energy. At this point you have 0 energy. That kind of doesn't make sense, right?
I mean,
yeah.
I can show you afterwards.
Yeah. Okay. Yeah, anyway, we will know when we do this. Okay. So it's possible because there's a differential of time, there's a differential of space. So somehow 2 differential, if it's just 1 differential, it's out of phase. If it's 2 differential, it could be in phase or phase difference of pi. So, okay, later we will see. Okay. And this one, okay, so if we want to make these 2 terms look identical, what we can do is we can let just define something like this. And how would that make sense? Okay, you might ask. Well, first of all, for the light, we have frequency, right? We know what's a frequency. We have the field. We know this constant. And the field itself has amplitude, right? This is actually a free parameter. For the light, there's no mass. Okay. So here, this mass is simply to match this one. Okay, if you say the mass is 1, then that's fine. If you say it's 2, then A is reduced by square of 2. Okay, so this is a free parameter we introduced to our system. It doesn't matter what it is. Okay, we just want these two to look similar. That's all. So this is kind of like yes. Okay. So A, let's write it down. Don't think there's a 2 here. Okay. We have A is okay, so this is your A. So by doing this definition, okay, introducing a free parameter here, what we are able to do is we're able to do the Hamiltonian of a EM field. The first part now is 2. Right, we get the first part, which looks almost it's identical to the. Oh, okay. I think I make a mistake here. I shouldn't get this in. No, it's correct. Okay. Okay. So this part equals this part, so this insert in here. Okay. Yes.
I'm sorry. In the middle of the board there, you have the H equals the.
Oh, this is Hamiltonian. Okay, yeah.
Yeah, so the H on the left-hand side is the Hamiltonian, on the right-hand side is the magnetic field.
Yeah. And let's do it this way. Okay. Okay. It's easier to do it in computer. Okay. You can say capital H, or you can change your font. Okay. So now let's work on this part. Okay. If the harmonic oscillator is the way we quantize our EM field, then the H should naturally come out as this, because H is solely determined by E. Right? There's no additional parameter you can add in there. Okay. We already use omega. We also use M to get our A, and if it works, it works. If it doesn't work, you have to stop here. Okay. We have to, think about other method to do the quantization. Okay. So now let's do the H. Okay. Okay, this one we know it's often I don't know if I need to do this math on the board, because I assume actually you all learned this in your undergrad, but of course it's very high possibility you forgot. Okay, so hx xz is 0. We define the direction. Okay, So all the h is in this direction. Okay. And we know the outcome is the same direction as E. Right? E is only at x direction, so we only pick out this term. Okay. When you pick out this, you do this. And I think there's a minus sign here. Just try to make sure. Okay, this is this equals to differential of t, epsilon 0. What is E now? E is A qt, derivative of t, okay, and then sine kz. Okay. So a natural solution for this, if you look at this, if h is proportional to cosine kz, right? When you do differential, k comes out, cancel it, and then there's a minus sign come out, cancel this one. Okay. So it makes sense. Your h equals to and then k, this one a cosine kz, and then q. Okay. I think I forgot epsilon. Oh, epsilon is already absorbed. Okay. Yes, epsilon is already absorbed here. There's no epsilon. Epsilon is in the A. Okay. Okay, cool. So we do this integral. Okay. What we found is, first we know this cosine ks squared. Do this, we get a volume, right? It's the same. It doesn't matter if it's sine or cosine. It's the same thing. Okay. So what we can write down, I think we forgot it too. Okay. What we can write down is okay. We have half 1 mu naught and then k squared and a squared. We put a squared in. Okay. A squared is 2m omega squared epsilon v. Right. And then we have q naught squared t. Right, this one. And then the integral of cosine squared is half v, right? We already get this, half v. Okay. Now let's see what happened. So v canceled out, very good. 2 cancel out. I think, 1 second. It's weird. Oh, I forgot this epsilon. That's why. Okay. Yep. So epsilon square epsilon cancel 1. Okay. And then what you're left is half. Okay. We write down m q. This part looks like this one. Okay. It's not done yet, right? We have other terms here. We have mu epsilon omega square k square. Okay. And if you're familiar with Maxwell equation, you know right? Okay. And then you also know k, wave vector, 2 pi lambda. You can do some calculation with omega over c. Okay. So what will happen there is mu naught epsilon naught k square equals to omega square c square, that's this 2 term, divided by omega square k c square. Okay, so it's 1. Okay. So naturally, well, this is a really good sign here. Our H, the Hamiltonian, when we make the first term, look like this part, okay, the second term agree with this automatically. Okay, a very good sign. Oh, I should use Q. So at this point, it really doesn't matter if we use X or Q. They're just variable. Okay, they're the same thing. Physically, X means position, right? Displacement. This Q actually means nothing, right? It means the amplitude, roughly something proportional to the amplitude of your EM field. Okay, that's it. Okay, so so from this point, sometimes if I write X, it's the same thing. And so at this point, it's very good. Some people use mathematics. By the way, again, the Hamiltonian here means the energy inside your cavity. Right? The Hamiltonian is the energy inside the cavity. Okay. So now you have the Hamiltonian. The first thing you can do is to plug into Schrodinger equation. Right? You define a wave function that you don't know what it is. You just know if you have Hamiltonian and if you want to do something quantum, you can use Schrodinger equation. Okay? And what this means is actually something pretty deep. And a matter of fact, maybe a lot of people actually, even working in this area, don't know that clearly. So I think when Schrodinger first write down Schrodinger equation, actually he doesn't understand the wave function. And then Heisenberg, let's see who visit whom. So Heisenberg, I think, visit Schrodinger, and then try to convince that your Schrodinger equation is not correct. My Heisenberg equation is correct. And then Schrodinger gets so angry because he couldn't explain what's the wave function. Okay, that's the biggest loophole in his Schrodinger equation. What is the wave function? And then he was actually sick for about 6 weeks, because of getting angry. Okay, and well, that's not terrible. You guys all know Boltzmann, right? Boltzmann, people don't believe his entropy, and then he killed himself. Okay, so so that's why we work in experimental physicists. We work experimentally. Nobody can question you. You can ask him to join your experiment, take photos, take videos, and then see it work. Okay, it's your business to explain why it worked, but it worked. Okay, and then he will kill himself. Okay, if he couldn't explain. That's why I don't want to put the camera there. I have to cut it out. Yeah, just add 10 minutes work for me to find that section and then remove it. Okay, Schrödinger equation. I hope AI can do it. Like I repeat the same word and then the computer find it automatically and then cut it. Okay, so Schrödinger equation. We don't have to know what is a wave function. We know it's some wave. Okay, probably describe how the light move. Okay, and then we know the eigenstate. Eigenstate is when you write down something doesn't change with time. This is use a symbol. Okay, doesn't change with time. And there's the oscillation part. Okay, so what this means is that if you put your system in this state, it's stable. It doesn't evolve with time. Okay, no matter what's the spatial distribution of your wave, simply doesn't change. Okay, and then if you do this, you plug this into here, you get your eigenstate or eigen equation. Okay, you simply plug this in, and then H come out, E come out, and then cancel this and get this. Okay, we talk about this a lot. You might not understand what it is, but the solution means there is a state that is stable in your system, and then that state has the energy of En. Okay, that's it. And also there's a kind of an excuse instructor always use is thanks to Richard Feynman. He once said that if you think you understand quantum mechanics, you're crazy. Okay, and then so that's something we can use sometimes if we don't understand anything. We don't understand something, right? So for this type of Hamiltonian, mathematician has worked on it, and the eigenvalue is okay. And in case you want to know what is the state, let's see, write down as 2. Well, we have H again. So, well, I hope people can be more creative when they with symbol when they write these equations. But this is kind of, I have to keep using their symbol. This is Hermite polynomial. Okay. Okay, so this looks terrible. If I tap, well, all we have done here simply, in some mathematical way, convince you that if you accept Schrodinger equation, which you should, okay, been proven almost 100 years, then your energy is discrete. Okay, you have energy discrete level. And what we mean by a single photon is when n equals 1. That means the energy inside the cavity is h bar omega plus a half. Okay, the half is vacuum energy. It's something weird. We will talk about it. Okay, and if you want to know what the wave function looks like, you plug in n equals 1, and then you kind of get it. And it's a lazy way to do it. It doesn't help with our situation. Okay, it really doesn't help. Why it doesn't help? Because can you write down E? No. Right? No. Because E is this Q. It's not a wave function, it's Q. Q is here. Okay? Unless you have a magical way of doing an inverse function, okay, which is extremely hard. So this is a good solution, probably for harmonic oscillator, but it's really far away from being useful in EM field, okay? Simply because you can't write down E, even you know the solution, okay? Oh, I should write down E here. So next we do something a little bit crazy, and then if we are going to, if this is in a physics department, then kind of what's following would say, particle is not particle, particle is operator, and that's actually the modern understanding of particles. They are operators, quantum mechanics operators with certain properties. And but here we try not to get into that direction, but we have to use operator anyway. Okay. Let's think about what would be helpful for our system. What we want to solve is simply atom absorb a photon. Okay. The E field lose 1 photon energy. That's it. We simply want to know that. So some physicists think, can we have an operator, okay, operator, when we multiply it with the n state, which means you have n photon inside your cavity, it goes to n minus 1. You lose 1 photon. Okay. That looks useful. And the Hermite conjugate of it, because it's quantum mechanics, we know that it should do the inverse operation. It should do this. The inverse of, this is called annihilation. Inverse of annihilation of a photon is a creation of a photon. Quite straightforward. And next, the thing we want to do is, first we need to find this operator. Okay. If your math is good enough, you can actually try. Okay. Here's n. You can write down n minus 1. And then you can inverse solve it with O. Okay. I don't know if the first person who solved this problem used this method or not, but I remember in my undergrad, the professor actually showed it once, and then I don't understand at all, okay, because of this function. Okay, take a look at it. Okay. I mean, if you're able to do it, I probably can waive your final exam. Okay, if you can find the O using this way, because you apparently you understand a lot. Okay. It's tempting, right? Well, something attempting usually is a trap. You might lose hours of time. You can probably watch a movie and feel good instead of you work on this like 3 hours and feel bad about yourself. Okay, so it's kind of the same torture you go through with the final exam. So I would encourage you of doing this unless you're really. And when you do this, you cannot Google it. That kind of undermine everything, right? If you Google it, it's not your work. So so let's continue with this. So from this point, starting from this, Q n goes to P. Okay, we no longer use Q. Q, well, doesn't have a physical meaning, so it's difficult to check whether our result is correct or not. Okay, it doesn't have a physical meaning. So what we do, because we know if you can replace Q with X, that's harmonic oscillator. We kind of can check the dimension. We can check a lot of things. Okay, and then m times x derivative of time, this is velocity, and m velocity is momentum. Okay. So from this time, we work on this. So now let's think about what's, when you look at this, we make some dimension guess. What is the dimension of O? What is the unit of O? The unit of wave function is 1, right? It represents probability. So when you convert a unit, well, when you convert 1 to another 1, you must be 1, right? So this one must be dimensionless. Otherwise, you cannot convert. Otherwise, whenever you do an operation, you convert it, then also you create some unit. Let's say if you will guess this is x, then sorry, when you multiply this, this will be, position. Okay, you cannot do that. So we know it's not x, it's not p. Okay, the only two operators we have here are actually x and p. All the others are parameters. Okay, so let's see. So okay, is there anything more we want to say on this? Nope. Okay, then we can. So now what we know is O is dimensionless. O is a function of x and p. Right? It's an operator, and the only operator you know in your system is position and momentum. Okay? There's no external force. Okay, if there's external force, then yeah, you can use that, but there's no external force. You're just having a photon in a cavity. Okay. So the first thing, so if we want to make a gas, then let's write down this A. A is the annihilation operator. It's kind of commonly used, through the area. Everyone knows A is photon. B is phonon. For some reason, I don't understand. So if you will have to guess, you start from the simplest one. Okay, linear combination between X and P with a parameter that make it dimensionless. Makes sense, right? You want it to be dimensionless. You only have two choices, and I bet most people won't believe it's just X or P. It won't be that simple. Okay, linear combination. Okay. If it doesn't work, you go on with adding X squared, P squared, or even adding XP times together. Okay. If it doesn't work, you keep on. Okay, this is a gas process. At some point, if it is so difficult, then you return to here and then you solve this. Okay, using a mathematical way. Okay, this is your safe net. Okay. But if you do it that way, you probably have to share your credit with a mathematician. So now let's look at what's this, beta x. So so we know the unit of Hamiltonian. Okay. No, this is not Hamiltonian. Okay, unit of Hamiltonian here is energy, right? Energy is h bar omega. That's a unit of energy. And then the unit of x, this is same as right, same energy, they too. Okay, same dimension. What it means is that 1 would be right. Okay, so that gives you okay. Dimensionless. And then you have the same thing for momentum. Momentum is right, this one we skip a few steps. We have okay, this is how you normalize this two, so you make it dimensionless. And then that's starting from here, it becomes possible to create an operator that make a system jump between state to state. So we write it down as A. Okay. So we can always have the first one, this place, we can always give a coefficient of 1, right? Because if it's 2, then you kind of have to adjust the ratio here. Okay, it's that simple. And also here, we say O operator on n state goes to n-1 state, but we didn't say equal to. So there's some flexibility we leave to ourselves. Okay, maybe there's a number there. Okay, it doesn't matter. Okay. So here we can put a 1 here. Okay. And the next one is 1 to m h bar omega p. Now, what's the coefficient here? Okay. One guess is just 1, right? Okay. Linear combination, easiest guess, 1. But then that doesn't work because position and momentum are real variables. Okay. You're able to measure them. So what will happen is x complex conjugate p, right, equals themselves. So you will have A equals A dagger. That kind of doesn't agree with what we want. Okay, we want 1 to be annihilation. Its inverse to be creation. So doesn't work. And the next simplest guess is, well, you want its complex. You want it to be a complex number, right? So when you do this Hermite conjugate, you create this and this to be a different thing. Okay. This is the next reasonable guess. Might not be correct. You have to check it. Okay. And then the only thing now we know, we can use is Hamiltonian, right? On this equals this. This is the only condition we know that is true. Okay, this is our guess. We want A to have the ability to do this. Okay, we have to calculate it to show, yes, this A is correct. Okay. So because we know what H work on the wave number, well, we know what H work on an eigenstate will give us. So the next reasonable move is to express H with A. All right, H right, you have X and P. Well, you can express X and P with A and A dagger, right? So naturally, you can replace X and P with A and A dagger. Then you kind of will start to see what, let's say, X squared. So probably you will have this, you have this, you have a lot of term, and then you work on a state, give you this, right? You start to know some property of what A and A dagger would do on an eigenstate. And then our final goal is you can show this. Okay, our final goal is to show this. Now, to express X and P with A and A dagger, quite easy, right? You plus these two terms. This cancels, give you X. You minus these two terms, cancels X, give you P. Okay? So we'll skip those steps, just give you the answer here. Okay, P. Okay, simple, very simple. Plug in this to this, and then we probably should calculate this a little bit. So first term, square of x, m cancels m, omega cancels 1 omega, and then you're left with h bar and 4. Pretty cool, because this one already gives us the, the energy unit, okay? And then a dagger square, that's the x term. So you have a square plus a dagger square plus a dagger plus a dagger a. Okay. You might ask, can I combine these two? Can I say this equals this and give you a 2? Unfortunately, you cannot do that in quantum mechanics, and later I will show you why. Probably next class, okay? And this is actually the starting point of Heisenberg's equation. So Heisenberg figured out you cannot switch operator, okay? And that goes to Heisenberg acidity principle and the Heisenberg equation, and that's equivalent to Schrodinger equation. And unfortunately, Schrodinger never understand that. Okay. And the person who unified their two theories are Pauli. Okay. I think at the age of 25. And then you do this square, I square becomes minus, and this cancels. There's a 4 here, and then h bar omega here. Also very good. Okay, and then this you get a dagger square, and then minus, right? Okay. In case you're a little bit afraid of quantum mechanics, just assure you that you can do plus and minus and cancel these two terms. Okay, there's no problem doing that. You just can't switch the order. Okay, so these two are the same. You cancel them. Okay, minus sign becomes plus sign. Okay, so you become half h bar omega. Okay, this is exciting now. A dagger a plus a dagger. Okay. Now let's look at this. H bar omega, very nice. We have so we already say h bar omega is very nice. Okay, we have the energy of 1 photon. Okay, well, it's very apparent in its Hamiltonian, which is a good thing. You don't need to go through the, heavy mathematics, calculate the Hermite function, a lot of them to get to this step. It's already showing here. Okay, that's good. And what's even better is that there's a half here. Okay, there's a half here, and later we'll see this is vacuum fluctuation. Very straightforward. So this is a step called, so we'll stop here, mathematical stop here, but I want to mention a little bit of what this operator action mean in physics. Okay. Now you might heard news about like Nobel Prize, right, awarded to some scientists because they discover a new type of quark, a new type of particles. And what is that particle? That particle is an operator like this. Okay. So, and how you measure something is you have a Hamiltonian. Okay. You have a particle, and then that particle disappear. Okay, and create something else. And you measure that process to confirm with you that, well, there's a new particle we observe, because there's no other physics process can give you B. Okay, the B is something you can measure. It's usually neutrino. There's electron, all kind of thing at a certain energy level. Okay, so this is second quantization, and this is people are still using them right now in theoretical physicists. Okay, that's all for today. Okay.